Okay, all right. So I'm recording now. So your just the symbols you're asked to write there, right? But I have the solution anyhow, as best as possible. All right, so this is the system. You would have now move on to the next page where you draw your free body diagram. So let us move over to that page. All right. Now, so as it said before, let me just shift this. How many persons are out? Okay. All right. So as it says here, right? So the first thing we do, we need to find it asks us for the position vector. And it says pointing away from B. So you're automatically going to write your position. So what are the coordinates? So you would have written down the coordinate of B, right? And you also write the coordinate of C, right? Can somebody tell me the coordinate of B and C? Who remember it? All right. So you have to write those down, right? And therefore you come up with those values. All right. So, all right. So let's look at B first of all. Let's look at all of what we are given. So we know that this is 12. This is 6 coming up here in the Z. And we know for C, right? C is 8, while B is 4 from here. But 4 in which? 4 in the Y. And 8 in the Y also. For C, 8 in the Y. All right, so let's concentrate on one at a time and look at what are the components. So let's look at X now. So if you, for the X, what's the value for B? So in terms of X, where's X? X is here. So B, we know that this is 12I, right? And for your Y, it's going to be 4, right? So that's 4J. All right. What is your Z? Do we have a Z component? No Z.
No, sir.
No Z component. All right. So that's 0. All right. And the next one for C, you have what now? You look across here, you see in the Y, you have 8, but what is the X? So we have an X component for C. Yes or no?
No. No, sir.
Good. There's no X component. So this is 0I plus 8J, right? Plus, now what else do we have here? What is the Z? Do we have a Z for it? Look up here. What is it that we have here for the C? Don't it have a 6 up there? Don't it go on 6 up to C there? You have to look, concentrate. All right. And a good way to do it, as I always tell you, now we need to find what now? BC we're finding, right? So what BC is going to be equals to now? Is it C minus B? Is it that?
Yes, sir.
Good. So therefore, what you write is, you could write it this way. For those who, you know, this might help. So as a relative position. And then you write the B, which is 12, 4, and 0. And so from here now, you get that this is minus 12I, this is 4J, and this is 6K, right? So from there, you would have got the position vector, right, that you need, right? So there you get that answer. Now that you have the position vector, you are to simply to go and use your square the quantities because you want to get so you're gonna get the modulus value, which is of R, in order to get your unit vector. So you'll be moving over now to get your unit vector, And the unit vector, we know we square these quantities, and therefore, so as a lot of person did it. I must say that what I realized is that persons were sometimes not concentrating, because just a simple squaring of these quantities, some persons got it wrong. But once I see that they have the correct thing above, they got the answer. Even if their final answer, some persons got 9 and all sort of stuff. When you square these values, I think you got 100 and let me get that calculator out. Just give me a second. So when you square these, you'll get 1.4, right? Plus 16 plus 36. That's supposed to give you, I think it's 160 something.
196, sir.
196, sorry, yeah. 196, yeah. I'm trying to remember it. And then you root that, you get 14. All right. So what we expect you to do here now, so you got that, and that was one of the things that was asked. What else was asked? So let me just see, because I didn't have the question. Need to be looking at it. So this is, so there you got the position vector pointing away from B. And that, but the right, and then you are now to express the tension in the cable, right? So once you got the position vector, you would have gotten your 3 marks right here. This stage now is helping you to actually get the unit vector aspect of it, where you can now find the force, because your force here is going to be equals to what now? So FBC is going to be equals to what now? The unit vector time F. You see, right? But right, so it's time the F value, you get that, right? Actually F, actually, right? So that now, so it means that you need to do is multiply 2 by your unit vector. So it's all of the value up on 14. So it just simply put in the modulus, divide the modulus 2 by the position vector, which is this here. So this is equals to 14 divided by all of these quantities. So right here, so you would have got the tension, and that was, how much marks was that again? That would have been 4 marks. So once you have the formula, especially, I normally give a 1 mark for that, and then have this value here, then you get full marks immediately, right? Straight off. All right, the next thing that they ask for, right? Where are we? It says, probably need to copy this. It says, state the unknown for the system. Now, what are the unknowns? Can somebody tell me what are the unknowns for the system here? But remember the question, can tell me the unknown. If I can put it right here. Do I have a pasting option here? No, can't. I'll keep everything. So right, so let me just paste it. It's the question somewhere over. Right, so what are the unknowns? Can anybody tell me what are the unknowns for a system like this? What are some of the unknowns?
So you have reaction in the AX plane, AX.
In the AX.
Yeah, AX is unknown.
So, all right, so we need to move over. All right, even though I wanted to go through these expression before, where is the expression part come? It says write the set unknown, then write the set of freedom. So you have a reaction. Let's just look at the reactions here. Look at some of them from this one. So here you have them. For right here at A, you will have a reaction AY, AX, right? I didn't write them already, so just to show you them. So they're right inside here, right? Would you have any reaction in the Z? Would you have any reaction in the Z?
No, sir.
Why?
Because we call it, it's moving, it can move. There's no
Right. So
reaction.
it says in the question, where is it again? It says the color, where is it again? It says something about color moving through. See that? Smooth. A. So this is A, smooth fixed square rod, which is fit loosely to it. So it means that there's no friction there. Right? So that's the part. All right. So this is here I want to show. So the reaction here in the Y, you'll have a reaction in the Y, you'll have a reaction in the X, but none in the Z. Right? Come on. None in the Z direction. All right, correct. All right, so that is, so one will be AX, one is AY. Also, the moment in MAY is one of them. Moment in MAX is one of them. And the moment in the Z is one of them. So how many you count so far? And of course, you would have identified this unknown already. We'd have found it. We find this one already, right? But this was the force actually going down. This is a little bit lean. This is going at some point here. So we have to just consider it. Right. So we have MAX, MAY as unknown. And in the Z, so we have 3 moments and 2 reactions. All right. What about the tension? Do we have any tensions that are unknown? Do we have any tension that are unknown? Yes or no? Do we have the tensions?
I'm not sure, sir.
You're not sure. But we have,
Sir, tension B.
see them there? You have, so we need a tension FBC, right? Which is referring to, so FBC is not known. So we need FBC, which is the tension going in that. Right? So, but we have actually worked out a value here, but is this the correct value? This is all right. All right. So now it says, so those are some of the unknown. All right. The fact that you have a force here, F, which is these values here. So this force here is actually in it's part of the system of forces in the diagram. Now, if you look at your force here, you'll see that it's in the Z direction, it is minus 75. So right there, so you know that there's a component minus 75 here. Now, when you formulate your forces from here, you consider what? You consider the X, some of the forces in the X, you consider some of the forces in the Y, and you consider some of the forces in the Z. So see it here. So in terms of your equilibrium equation. So the equilibrium equation, we need to find some of the forces in the X. Those are some of the unknown. Some of the forces in the Y, unknown. And also the moment. So we have 3 moment forces that we don't know that we need to consider. And we need to consider the tension also. So we consider moment and tension. Those are basically the unknown in this. So it's actually 6. So 3 forces, 3 moments. All right, so that's basically what they're asking for. They say state the unknown in the system. Most time, once you write the equilibrium equation, then you're right immediately. Once you write some equilibrium equation, you're gonna get some answers. Right? So that's all. The question is leading you on to consider equilibrium equation. When it says state the unknown, they are considering these: sum of f of x, sum of f of y, sum of that, and also the sum of the moments around A. So we're focusing on A, right? All right. So for the first one, what we did now, we sum the forces in the X. So now remember, now we were focusing on this one first, and we have some values here. So this, the position vector give you the force FBC in terms of the unit vector, but we don't actually know all the values. Now you need to find the individual values. Some of the forces in the X, right? You would have looked at your X reaction, which is here, going that direction, right? Plus 20, right? So 20 here, right? Right? And next would be your what's the next one now? So you have 20, then you look in here, you see you have this value here. So you subtract it from the 20, right? So you subtract these two values here. So you have this value here and that value. They are all subtracting from your reaction AX, right? Anybody have any question right there? So this is positive, this is minus. So it's a matter of these adding to this value here for a reaction. The same thing here, you have a reaction. So where's the X again? The X was coming this way, pardon. Let me just draw it back. The X was coming this way. Let's see if I can get my writer here to work. So the X was coming this way, and the Y is this way. So this is AY, and this is AX, right? Right, so it coming this way, so that you have, so the AX is 20 from plus this value here from the reaction. So you add all of those, and that gives you your equilibrium equation in terms of some of the forces in the X. So you have a force here, you have one over here from this, and you have one from here. So all of the forces in the X. So you have a component of a force over here, a component is down here in this force, and this one. So you add them all together. So it will be adding the 20 here, which is from this force, the force component from this one that you found, which is this one, right? So you're adding all of those reactions together. So you have the AX, right? And that gives you the first one. The second one, you're gonna do the same thing. You're gonna add this value, because that's, you have a AX component here in this direction, not in the Z, of course. Here's a component from this, which is over here. So this is it. You're going to add this one, plus this one here. So you had all of those. So you'll be looking for components. One, all the components in the X directions, first in the Y direction. So the Y is AY minus 40 plus this component here that you just find, right? So you're all of that. Now, what about the Z? The Z also, there's no reaction here because the color is smooth, right? But of course, we have to look for everything that. So we have this value here and this here, right? So there's no reaction there, but we have these minus 75 plus this component. And from there, you can simplify an FBC actual value from that. So it becomes what? 175 FBC. So that's an easy way to find it. From just having the position vector, we can actually find its value right here. Because remember, all along we don't know the value, you know. We don't know it, right? We have the position vector, and we combine the position vector with the unit vector, and we have an expression which represents it, but we actually never find it. So you have that equilibrium equation, that one. It says always a system of equations. So the unknown, three unknowns that we have here in terms of force help us to find FBC, which is that force, right? Any questions so far? And the fact that you get this now, you can use this value here in this expression up here. So you'll have put back the 175 in this expression here, and you got the value for AX and AY, which would work out to the 130 pound and AY as minus 10 pound. Any question there? So that's how you would do that section. All right. So those are three unknowns. You have actually found three unknowns, right? So we need reactions, right? So hear me now. Whether or not you gave me, once you gave me some unknowns, I would give you the answer. If you write down the reactions, I would give you the answer. If you write down the moment expression, I'll give you the answer. I was hard and fast with that, right? So if you just wrote down sum of X sum of y, sum of that, and the moment, I'll give you the answer just the same. And if you write reactions, I'll give you the answer just the same. And write moment. So I was not strict in terms of what you write here. All right, let's left to your interpretation. All right, let's move on. All right, what about the moment section now? So it says, the part of the question here says, write down a set of equations that will use to solve the system. Do not solve the system, right? You just need to write down the expression. So let's move over to it. It never actually asks to solve them, so let's look at it. So we had actually wrote these down first. We used those, and we got that value. Remember? Hello? Someone said something? Hello? Is it that someone saying something, please? Hello?
No, sir.
Okay. All right. Let's go. All right. Oh. All right. I'm having a little aches and pain, but nonetheless, I will try and continue. All right. All right. So now we are looking at some of the forces in the x direction. All right. Some of the forces in the x direction. So this is the x. Where's the x direction? All right. So when you take moment in the x direction, where is it that you would normally look to get your moment in the x? When you're looking at your x direction, can somebody tell me how is it that I would now be using 6? Let me bring over an expression here that is relevant. Let me just write down let me get something over here. 1 second. I'll keep this expression here. I want it around here so we can look at it and it tell me what you this one here. Let's bring it over, put it somewhere right here, like right here. Okay. All right. Big question now. When you are finding the sum of the moment in the x, can somebody explain to me how is it that I got this value here? Now see that you have, this was your force, right? Your tension, expression for your tension, and you have your x component, y component, z component here. All right. So we always tell you that you need to write. Pardon me? Come again? Someone saying something? Hello? You're not hearing you again. You're probably muted.
They look like an accident.
Oh, but I need to have a discussion, so I want to see if you understand. So now we're doing all the forces in the x. One of the things that we always do, you need x is in that direction, so you write it down, right? So we now need to take moment in the x direction. So we're going to look for a force. Force 6 upon 14 is what? What component is 6 upon 14? It is in the y, don't? Everybody see where the y is?
So Z.
So
Z.
look, no, sorry, z I mean. You look where the z component is, sorry. So you see it is in the z. Remember now, let me just draw the arrows, show you. See if I can get that right. So you have a component that is gonna be in the z, you have one in the y, and you have one in the x. That's the x, y, and the z. Now, the fact that this is in the z, one of the rules when you're doing moments is that your moments plane. So if you have a moment here, see if I can get I need to draw a diagram here so you can understand what it is that I am saying. Because let me get that. Right. Get another right. All right. So let me draw it. What is the principle here? The principle is, and a lot of you may have missed our class, the principle is this is in the whatever direction your moment is, your force and your distance will be in a different plane. So if your moment is in one plane, your force and your distance must be in a total different plane. So the plane that we're in here, whatever plane it is down here, your force and your distance is in this plane, but the moment is in another plane. That principle is what we'll be using here. So now we want to find our moment in the x direction, right? But it therefore means that our force must be in the z direction, right? And our distance is going to be in which other direction? Probably y direction. So let's look at the components that we have. So we already know, right? What was our position vector again? Our position vectors, our distance, pardon me. Our distance here is 4, this is 12, this is 8. So your component here, this component is going in this direction, right? And your distance is in this direction. So this is 4, this is your FBCZ. So your FBC Z is in this plane and this one. So the plane that we're actually having here, this is like this, something like this. I hope I can represent it properly. So this is your moment plane, and this is your force plane, and the distance. Let me see if I am representing them correct. So this is a force, sorry. And then this is your distance plane, right? So they are actually into a different plane from the moment. So here you take out this value from here and this value. Of course, you will also have to consider whether or not the moment is positive or a negative moment, right? So if it's a positive moment, which direction is the F going? Can you remind me, which direction do we consider as positive, class?
Anti-clockwise, sir.
All right, so if we consider anti-clockwise, let me see. Anti-clockwise will be that direction, that the force. So the force is going up. If the force is going the opposite direction, so this is positive. Let me see if we are getting direction correct. So your force is going up, your body and your distance is here. We are turning it what? Clockwise or anti-clockwise? Let's see, what do we have here? So we are having it going in our, it's really 6 upon 4 times 4. To me, they have it here as positive value. Let me just check that. Yes.
So can I ask the question? So if you're finding moments in the x at the x-axis, the force axing the z and the distance axing the y in all cases.
Yes. Of course, one consideration that you'll have to think of is, as I'm looking at it here now, to say, in terms of what is represented, what I've written in front of me here, right? As I just transcribed from somewhere else, is the actual value of the moment. So if the turning effect of the body, so if it is turning, if the moment is turning this way, it's supposed to be positive, meaning that is force times distance. So we are actually saying, so I'm just looking to see where is the positive of FBC would be which direction? So up is positive, down is negative, correct? So the force now is going up, right? But the distance is here. All right. So if we were to do it the other direction, just checking the effect of the force. Right. So you have 6 upon 14 times FBC plus positive times 4. And you'll end up to get a negative moment. So the moment that you will get in there is that the moment is going into the clockwise, so to speak. And I'm concurring because when the body is going up and the force is here, you're going to get an effect of it turning into the clockwise direction. from this. So it's 6 upon 4 times 4. But this will tell you, once you work out, so you'll have put your, notice this is going in the positive moment direction. So you'll have write that down. Consider your force, which is 6 upon 14 times 4. So it end up give us what now? A clockwise, which is minus, which is correct because the effect would be going up and the force is here. So you'll have just simply write this down because this is positive and this must always be written in your expression. Then now you put the force in 6 upon 14 times the distance. When you transpose that, you'll end up with a minus, which is telling us that the body is actually spinning that way, right? And that way would have been a clockwise, which is minus. All right, so let's go to the next set.
Hold on, sir.
Mm-hmm.
So, all right, let's say that we are taking moments at the y-axis.
At the y, where's y now? Y is right.
Right?
Here. Sorry, why up here? Why not x?
I just want to understand, sir. Where would we, in what axis would you take the force from and the distance from?
So look, clearly, this is x, this is y, this is z component of the force. But it is from this component over here. All right. So it would be, so this will be positive, this is positive y. All right. So positive y is that direction. You have the distance here. X is this. So look at this is the axis for these components. So FBC, this one is gonna be up here. 6 upon 14 will be right here, right? So the effect of it is right there. So it's going up, but then now it have a distance here. It is going to know. All right. So what is happening? Let us look at it clinically. The fact that it's going to be coming off this cable here, it's going up, but it's distant, routed through to the distance here is what now? So this is what value we say we have 4, which is y. So it's z times y. Right. So the effect of it going up and the distance is this is 4, right? So it's really going to be turning it into the clockwise here. So it really makes sense. Look at it. So it's 4. The effect of it is 4, right? Look. 4 here.
So the distance is 4, sir.
The distance is 4. Yes, man. The distance is 4. Oh, you never see that. The distance here is 4. The Z, see the Z component over here? The Z component here is this. Look, see it over here? This is where I'm marking here.
Yes, I see that.
Yes.
I see that.
So it's going up. So that gives you the right angle. You see the right angle here?
Yes,
so
sir.
you see the moment angle, and that moment angle will turn the body where? That direction, or so.
Yeah.
So that is what? Anti-clockwise. All right. So anti-clockwise is why we get this value here. You see that?
Yes. So you're talking about the y, the x-axis. That's when you find the moments at the x. I'm talking about
the component what we are using. Remember, the force that we are considering here is up here. How can let me see how can I show it to you better? Hang on. Let me see. So what I'm saying here, this value up here is F, B, C, Z. That is that. F, B, C, Z is that here. Where's F? F, B, C, Y is that direction. And F, B, C, X is this direction. So is this one up here? Come on, right? I don't mess around. Discard. No. What should I? T. Let me go back up because it want to. Hang on. Let me just see if I can get it this. All right, so it messed up the thing a little bit, and I can't get it off. Right, I'm not gonna try. All right, I might just remove all of my drawing. Or do you want me to draw it over? You want me to draw it over just to show you?
Sir. You're good.
I want to clarify now. I want to make sure. The fact is that it actually see up here now. But all right, what I'm saying here, so the component of BCZ is over here, and these components are over here. The 3 components are acting off this cable, right? And but the distance is gonna be in this 4 here. Time I touch it, it's jumping all over the place. Pardon me, but my device giving me a little bit of issue. All right. So here, the 4. Can you see where I'm pointing? Anybody seen my pointer?
Yes, sir.
All right. You see this 4 here? This 4 is this 4.
Yeah, I get
So,
that.
right. So you see there, this is going up. This 4 is right along here. So it's going to turn it about this point. Which point is it turning it? It's turning it about here, that point here. So it's turning. This is now this is acting. This is the origin, you know. Remember where the origin is down here? Can I get the writer back? My writer seems to be messing around. Hold on. Come on. Let me check back my writer. Please. Let's see if I can get it. So, right. So once I'm writing, I don't have a pointer. That is it. That is the truth about it. So here's the origin. So it's acting around this point here. So the body is turning around here. So this is your point that is the moment is acting from, the origin, right? So the force is going up in the Z direction, but the distance is 4. So see there? So this motion is really a anti-clockwise moment. But at the end result of it is giving you a what? A minus moment, right? When you're finished, because you always write this. This is a positive. MAX is in the positive moment direction. You see that? Because in the X direction, you're going to have a positive moment. Then now you need to actually find the moment. So you're going to take the component from your force vector. Always look for your component in your force vector. And then now the next thing you have to do is look for your distance. So we have identified 6 upon 14 is the Z. If you are in the Z, you're going to have to look for your distance now. So this is the Z going up here. So it's ZY. So the moment here that we have is what now? This is force times force in the Z direction times Y, right? So that is what end up giving you this moment here. So moment in the X is really a result of Fz times Y distance, right? So that gives you, so it's Fz times Y distance here, that moment. So look, so if this is a Z and this is the Y, where's the Y? The Y would be this diagram is a little bit different, right? But all that I want to show you is that wherever the force act, the moment must act perpendicular to it. Right? So Fz times Y will give you moment in X. Right? That is what we are saying. So otherwise, My, and I want you to tell me this, quiz now. If I am in Y and this is F, what forces would need to multiply to give me My components? Can somebody tell me? What force and what distance would I use to get moment in the Y? Next question.
Would you use the force in the Z and distance in the X?
There's a force in the Z and the distance in the X. All right, let's look. Let's check it if that's the case. So now we're going in the Y, right? You're always right back. That's where's the Y direction? The Y direction is going that direction. So it's MYX. You're always right back MYX here. Then you're going to look for all the components in, as you said, in the Z you said. That is the Z you said a while ago, you know. So we look for the Z. All right. So we have a number of components. So another component that we have is, so Z, that is 1. And we also have 1 from this up here. All right. So we have 6 upon 14 is a Z component. And we have minus 75. Do you agree? So we have 2 forces. We have 1 force here and we have 1 force here. We have FBC and we have F over here. So once you have, and I know you are not seeing my pointer. Let me get back a pointer. Hold on. Once I'm in certain modality, my pointer is gone. Hold on. All right. Let's go back. When I finish the discussion, what I will do is just switch back where I can write. So I won't write now. I just discuss. So all right, let's look at this one. So My is this direction. You're going in the origin. So the plane must be perpendicular to your, which plane we said? It's going to be, so if you're in the Y, if you're taking moment in the Y, you must be acting in FZ times X. Let's check it. So Z is perpendicular to Y here, and X is, where's X now? X is, so we have it, so it is this plane. So we have X distant here. X distant is what? 12. And we have 2Z component, minus 75, and we have 6 upon 14, which is another component for the FBC force. So 2 force component that we are involved with here. This 75 here and 6 upon 14 FBC. So 2 components. And the distance that we have for the both component is the 12 FT, which is between the origin along the x-axis. So the plane that we are focusing on, right, is going to be perpendicular to it. Anybody see it? I need to draw it now, just for clarity. Let me draw it. So the plane that we are working with, this is your moment, M-A-Y, and let me see if I can draw it for clarity. So this is it. So this is your distance, 12, and this is your F, your force. Anybody see it? So that is the perpendicular and that is the moment. Can you see it? So this is the 12 along the X here, and this is the Z. Who don't see that? So let's look at it now and do it. So the first one is the 75. The 75 is this one. So it's 75 times 12. I can't show you that one because it is positioned down here. I'd have to draw it. How do I draw that now? Down. I'd have to probably draw that down and show you that the distance is that. All right, so I'll probably just draw it down, a component of it. So it's time that distance, right? And you'll get the right answer, something like that, right? For that one, for the first one. And it is going in which direction? And that will be turning the body. The force is what now? It's minus. So the force is going down. Let me see what they have it here as 75. But the actual component effect of it is, let me see, which direction are we turning? So the component is minus Z. That means it's going down. Okay, so minus is coming down. So it's minus times plus, so you have 75 times 12, right? The effect of it is going to be turning the body in the clockwise. So if it's turning the body in the clockwise, but it's going down, it's end up going to give you 75 times 12. It's actually going to end up positive because it is minus going down. All right. So say 75 times 12 for that one. All right. What about the next one here? Let's look at this one over here now. The force component in the Z again, going up. This time it's going up, it's not going down. Going up over here. We're at this section here. Look at FBC line, please, the dotted line, broken line going up, right? And the component for Z is straight up here, where we have it before. So you know Z is going up, right? Times CM12. But 12 is not straight way this time. It is going which direction? That way, right? So that's where your perpendicular is this time around. Your perpendicular is there. So this is 12, right? So the 12 effect is coming from here. See 12 effect there. So it's going up that direction, and that is your 12. So it's turning into that. Look to me like what now? Let me see what effect am I having there. So this component is going let me see. We are going minus, right? That was as minus. Okay. What I think happening here, whoever wrote this may be writing from a different convention. I would actually put a minus here and a plus here, right? But it would work out to be the same thing, right? I just took this from another workout, but I'm just checking it for myself. So it is minus 75, right? Minus 75 times 12, and then I would put 6, positive 6 upon 4 times 12, right? So this would tell me that I'm getting a clockwise, which is, I'm using an anti-clockwise as positive, so that I would take it to be going up in that direction, positive, which is that. So see, 6 upon 14 is positive, around O, which is 12. So, right, so the convention used here is a little bit different from our convention. So ignore the sign a little bit, please. That is where our, but answer will work out to be the same, right? So you will end up to get 0 for this. So your moment effect for it in the Y is actually 0. All right. All right, so that is for the Y. What about for the Z? What is the, if I am going in the Z direction, let me draw Z, actually draw the Z up, yeah. And where it be what two forces would I be using for the Z? What will be the force that I'll be using for my Z? Possible force and distance. What possible force and distance would I be using for my? Would it be F, it's either be F, Fy or Fx, right, times Y distance. Isn't that so? Hello? Are you with me? What do you
Yes,
understand?
I think so,
Right.
sir. Yeah, man, sir.
Right. So you see the plane? So it's gonna be either a Fx force or Fy force times X. So if the force is X, the distance is Y. And if the force is Fy, the distance is X, vice versa. All right. So anyway, let's look at this one now. What we actually have here. Okay, you have to look at problem by problem. All right. So look at this one now. Fzx, which is what we're looking at now. Fzx, right? So you better write down this because where's Fzx? It's going up. See it going up here, so this direction, it's going right up there. So that is sum of Fzx here. And you write that down because you always have one that is you need to put in the equation. It's always there. So you put one there, moment factor there. Then now you're gonna look for this. So you have a force in X there now, you have a force in Y there now, which is M. You have 40, right? And the distance is going to be in your X. So see it here now. Look, let me see the convention. Based on the convention, what should we get in here? If we are using our anti-clockwise, this workout might be clockwise. All right, so you're gonna go up, and I'm just seeing that workout is in clockwise. So this is going to be going down. So that effect of that force is coming down right through the center here. Can I clear? Let me clean up this thing a little bit. Too much drawing here. Thing might be a little bit. All right. Let me just clean up a little bit. Just to get some so that persons can understand. Clean up here. Oh, some of these things not coming up. All right. All right. All right. So let's go back to where we are now. I want to just make sure that we're at the same page. All right. So now we're gonna be saying, so you have a MZ which is coming down here. So some Y component here. Where's Y? Y is going to be where now? From here, Y is going that direction. So you have 40. And hold on, where's the negative Y? The negative Y is this way. Let me just draw the rates. It's coming that way. Yeah, that's a correction. Look back at your diagram. Do you see where negative Y is and positive Y is? Look carefully on them, please. Everybody see them? So your positive Y is this direction over here. Can you see it over there? I know it's crowded over there. The diagram, I can't lose it because I actually save it. I try and erase it. Nothing can erase up it. All right. So in other words, this page is a little bit crowded. Hang on a second. Let me see if I can fix that. Page is very crowded. See if I can find this thing here. I want to get back this page here. We'll see if I can. 1 second. Oh, no, sir. I don't like present and it's crowded. All right, I want back this diagram. Okay. Right. Okay. So what I'm going to do is just put another slide in while we discuss it. Another slide there and the solution. Right. Right. All right. So that is it. All right. Where was our force now? Let's carry that over also. All right. So now we can look back at it. All right. So I want to be quick here. All right. So that is. All right. So we are the last section of this problem, and we just want to clear up. Now, as we were saying before, everybody can see the Y now, can see the values now. All right. So let's see we have right. Okay. So this is a positive of Y. That's Y positive. All right, so positive value of Y that direction, and this direction here is X positive. So we have to see that. So we already established that it is Z we are talking about. So it's F. So the Fy, which is that value here, right? And likewise, you have another one up here. But the distance we're talking about is in the X. So, all right, so we established that there is a Y component here in the negative Y. So it is some component over here, which is 40, right? And the distance here. So this is like how the thing would be. So it would be something like this. So this is be 40, this is 12. All right, there you get the moment, Z moment up there. All right, so the force is coming this way, right? So from that now, what can we say about the moment? Is the moment going to be clockwise or anti-clockwise? Best of your understanding. What would you say that the moment is? I would say that the moment is anti-clockwise. Do you agree with that? So I already told you that my convention that what I transcribed from this solution is that they were working it with the clockwise. All right, so that is, says 40 times 12 for that one. Then this one now, up
Sir,
here. Yeah.
sir, I think they have it as clockwise now, but I think it's because the negative times the negative 40. That's why they put plus.
The negative. No, what I am doing, look, they say this in the negative 40, and I already draw it in the negative 40. So I'm not introducing two redundancy in my problem. You understand what I'm saying? I actually draw it in the negative. You understand me? See the positive Y is going, the positive Y is going that way. So I'm not going to introduce a redundancy in my problem. You get what I'm saying? So the 12 is here, look. So the 12, so the moment here now, you know. That moment to me is a positive moment. So the body will turn. So the body turning that way. Right? So it is going to be the 40 times the 12, which is right here. Right? And then now the next part of the problem. So that is one part. But we have two other components to deal with. Let's look at them. Two components to deal with. We have these two components here. We have one for the F and one to the Y. So up here, so now, right, we have two components. So with one component in the X, where's the X now? So one is going to be coming this way in the X. This is what? F, B, C, X. That is that one, you know. We have another one, Y. Where's the Y one? The Y one going that direction. Is it positive or negative? So we have one F, FBCY is that way. So the positive are that way, but this is what? This first one here is a minus. So the minus would be, which direction will be the minus? Minus will be going that direction, that's all. Right? And then now, so it is force times the y distance now. So it's a y distance now. Whenever, so the force is in the y, so the distance is in the x, which is this distance here. You see that? You appreciate that? So the distance, see here now, this is the forward distance now, which is this distance here. That is relevant in the problem. So it's going to turn it about O. So also I'm going to say that it is turning it in which direction now? So it's going to be turning it in the, let's look. Oh, it's going to be turning. So one was turning it, the body, anti-clockwise, and one turning clockwise. So you have this one turning it. Okay, so it's going that way. Right. So I say, as I'm telling you, they use a different convention. So I would get that as minus. Let me just check if that is minus. One is plus, one is minus. Right? So one is plus, one is minus. 12 upon 4 times 4. And then this one also is going to be minus. So this one now is what? Value. This is the y. Where's the y? The y is this way times this 4. Right? And you would get the same value. So it's a 4 upon 14 times 12 for both of them. Any question here? Do you understand how we get this one? So this one now is the x. This is f of what? FBC x times the y distance. Can you see that? While this is what now? FBC y times x distance. So you see it? This one is saying the x times y, vice versa. And all you have to do, but you have to know carefully where your moment is turning the body, right? Right? So you have to look for your convention in terms of how the body is turning about the origin. Remember, that is the origin always, you know, always, you know, origin. So the body is turning that way, right? But for this one now, you have the body, where is it again? This is FBC for this one. So it is 12 upon 14, right? You have that positive, so you're going that. The positive, this value is minus. But let me see where we have this. So this is going, if it is positive, if they have the value as positive, let's say that it was coming this way, then it will be turning clockwise. Right? So this is minus, so it will be turning that way about the origin. So that is why I changed the sign to be minus. Right? The next one, let me tell you why I changed the sign here. There's 4 upon 14. Let me show you that a little bit clearer. It's a y distance. Where's the y? The y is going that direction, right? Which is positive times the 12 here. So it's going to be turning it to the clockwise also. And the clockwise is minus, and the clockwise is plus. So I had to change the sign around to make it relevant to our problem. All right. And therefore, you work out that you'll get 7 minus 7 is 20. You just have to look for the signs, people. Be careful. Be careful. Spend a little time and make sure that you look for where the direction of the force is going, and you work the problem accordingly. All right. So I'm going to move from this now. If there's no more question, once you got those, you'll get full marks. You didn't have to solve it. Once you're able to write, even just write the expression out, you'll get the full answer. You didn't have to solve it. So we didn't mark you for solving it, because I think the time, there's a consideration with time. So we just expect you to write it. And as you can see here, this is a clinical demonstration where you have, this was what? Fx, the force is in x, but the distance is in y. And likewise over here, the force is in y, but the distance is in x. All right, so this is clinical. So you need to look back at this line here and make sure you understand how that moment was taken, right? One is clockwise, and two is clockwise, and the other one is anti-clockwise. But this convention, whoever work it, and put the convention around the other way. It doesn't matter seriously, right? You could choose to make clockwise positive, and then you would get the same expression here. But if you're using anti-clockwise, you're gonna get you have to change these signs here. This will be plus,
It's been minus, that's been minus. All right, that's the only difference I'm seeing here. So I'm gonna move on. All right, so that is how you would do that. All right, so we're gonna move to question 2 now. How much time are we have left here? So we have 1 hour to go. We have question 2. All right, the first thing you would do here is to find the reaction forces, and I think this is normally the easiest part. So you have 20 force coming down. That it means that you must have a 20 force coming up too. All right, and based on how the problem is progressed, we had equal force at B and equal force at D coming up. So if I have 20 force coming down, 20 kilonewtons coming down, based on how it is spread along the beam, when you work it out mathematically, using your equilibrium equation, you're going to get that one here is 10 and the other one is 10, which I think is a basic that everybody should know. I don't know why I ignore not doing the workout, but all right. I will keep, and let me put in a thing here so we can actually, somebody can tell me quickly how to work this part. All right, so I will copy the diagram, and somebody just tell me how to work out this part here quickly without thinking twice. How you work out the reaction for this one, please? Can somebody tell me? I don't also want to do it, just tell me quickly, and we'll proceed. How did you work out the reaction here, which is normally basic, the very basic part of it? Everybody was comfortable with that? Do I have to go through that, or I should go through it still? Hello? Talk to me.
You don't have to go through it, sir.
All right, good. So, all right, I won't bother go through that. I will run across. All right, the beam.
No, so you go through.
Why? But that's basic, man. You guys
No,
should know that part. You
yeah,
don't want me
no,
go
sir,
through unnecessary or
got you.
something. Let me
Go
just
through it, man, sir.
go through it. All right, let me just drop this one right here. So I'm trying to paste. I'm not giving me a chance to paste anything in it. Once it is in the slideshow, I'm pasting it in. Right. Because I just want to work on the timing. Yeah, so I have that. All right. So you're saying the workout here, I didn't bother do it. All right, we just talk to you. So as you know, you can use your equilibrium equation. The sum of the forces in the x and the sum of forces in the y. Sum of forces in the x is 0, so you just concentrate sum of the forces in the y. Right? Sum of the forces in the y, it would be 500 minus coming down, minus 10 minus 5, right? And you would have put in your reaction force here. You draw your free body diagram, RB, and this would be RD, right? And so this would be plus RB plus RD, right? Equal to 0. That would give you what? Minus 20 plus. So you get your equation in Y. Right. Okay. On doing so, this is B. Of course, you would decide to take moment somewhere. So you could choose to take moment at B. If you take moment at B, then now you would get, so everything is revolving around B, taking anti-clockwise using our convention that we practice using. If you take that one, you'll get 5 times 2 positive, right, for the first one. And then what? No, you will be, so every RB is not in the problem, right? Because you're taking moment at B. And what's next, please? Can somebody tell me the next one? Say to be what now? Minus 10 times 2, right? And then the other one would be what now? RD is what? RD times 4?
Yes, sir. 4.
Is it positive or minus, please? RD times 4. It is positive. So that is the one, anti-clockwise. All right. And then the last one would be what now? Minus 5 times what? 6 equal to 0. And you just simply solve this. This will be what? 10 minus 20 plus RD times 4 minus 30 equals to 0. So here you would get what? Minus 10 plus RD times 4 minus 30 equals to 0. And for this one, you could just say RD is equals to 40 plus upon 4. So it's equal to 10. And then you just substitute it back in equation 1. So you would get RB equals to 10 also, kilonewtons. So it's 10 kilonewtons. Just run through it quickly. Right, so you just form those expressions. Anyway, I'm finished with that. All right, here now, what you would do, there in your, when we're doing it in the class, we actually discussed it a little bit different from how I want to approach it this evening. So as to kind of just help some of you to have a kind of understanding to the subject matter. Right, I had sent you a slide, which is a little bit simpler of how we do it when we're cutting it, just referring it the section to X. However, we don't have to do the X thing today because we actually have the distance to cut it to. So let's say that you cut it to a distance, whatever distance they have on this. That's how I'm gonna approach it. Fine, I'll just help you how to many ways to look at it. So let's say you cut it to some distance here, B, right? Over here, you cut it to this distance here, B. That means right here, so it's 2. And now the shear is always going to be up down. You notice all of them, the shear is coming down. So your shear is your first equation you're going to write. You have the normal. Sum of the forces in the X is to the normal, which is 0. The next one is sum of the forces in the Y. So look at all the forces in the Y for me, guys. So the Y is 5, and you have V. So it is minus 5, but the minus is coming down. Minus V equals 0. And that's for AB. So therefore, you get your shear as minus 5 kilonewtons. What about the moment? The moment in AB section, you must always write down AB, right? And as I told you, whoever do this, they tend to write some of the things in, they're using a different convention, which I actually bar. I bar the notes, but some of these things is in a different convention. All right? So the convention, sometimes I just didn't have the time to write out everything. So the convention here, so let's just look at it from what we know. So you put the moment down, so you know they have minus. Let's say I was to change that back to plus. That's for the moment. So you had a moment, positive. And therefore, our moment that we're taking now is going to be 5 times 2. So that is positive, right? See there? So I'm telling you that the person work the problem into a different convention from what I. So it is 5 times 2 because look, 5 times 2. So remember, I'm taking anti-clockwise as positive. You know what they're doing? See now having us says anti-clockwise I'm using. They have a different convention there. I didn't even realize. Up till now I'm looking at it. It's just realizing their convention. All right. So their convention, I'm using anti-clockwise as positive. So I'm just changing the sign. So this is 5 times 2 plus m equal to 0. That gives you a minus there. All right, so that gives you, clearly, you get your shear force and your moment for that section right here. You need to move on to BC. So we're going to say, right, if you cut it right at C, which is going to be AC, so you're going to have, that is 4 coming down. So how many forces we have here? We have 5 and we have the 10. And we have a shear force going down. Now, as I said, I'm going to change my convention to anti-clockwise, right? So anti-clockwise, right? So let's work it anti-clockwise. So it's going to be, and I'm taking my moment about this point here. So it's going to be 5 times 4. So it's 5 times 4, which is anti-clockwise. So that is positive going round, all right? And then the next force I have is the 10. If I'm coming that direction, then I consider I'm clockwise. So I'm going to be minus. So that is a minus there. So that is be 10 times 2 plus m. When you work that out, this will give you 20 and that give you 20. 1 is plus, 1 is minus, so you get 0. While your share, did I work out the share? The share is coming down minus 5, 10 plus 10 going up minus the share. So that gives you 5. So you're going to give you a positive 5. So you have both the values for your share and your moment. So you must know them. So those are what you're going to use to draw your graph. The next one, quickly now, you're cutting it where? Right here, 2D. So that is AD. But AD, onto AD is 6. You see that? How many forces you have here? You have 1, 2, 10 kilo going up. You have the 10 kilo coming down. And then you have the shear. So you have 4. So we can use our sum of the forces in the Y. The normal for all of it is 0. So I don't have to bother discuss that. Right? Remember the normal coming out straight is 0 in the X. So some of the forces in the Y, guys, come, let's go. Minus 5, plus 10, minus 10, because you have what? You have 1 coming down and 1 going up. So 1 is plus, 1 minus. Minus the shear force, which is always coming down, minus. So that gives you minus 5 kilonewtons. All right. The next part for the moment now. Let's take the moment. Remember, where are we taking the moment, guys? Just for clarity. Anybody know where we're taking the moment? Where are we taking the moment, class? Can somebody talk to me, please?
They're at the section that you could.
Ah, nice. Anybody else want to concur? Everybody agree with that?
Agree, sir.
So
Yeah.
that is where
Yes.
its 0 point is. Don't?
Yes, sir.
All right, good. Are we using our convention again? I'm changing the convention that is actually in the workout here. All right. So the convention now that they have, let's go for the moment. I'm taking anti-clockwise positive. So I'm going to go 5 times 6. But that is what? Positive, because that is positive for me. That is anti-clockwise. And then the next one is 10 times 4. 10 times 4 is minus because I'm going in the clockwise. Right? So I'm changing my sign. And then the next one coming down, the next 10 coming down is going to be positive. Positive 10 times 2. Right? And this moment is always going to be positive. So I'm holding it like that. Right? So therefore, that works out to me minus 10. So the two values that is important to me is minus 5 and minus 10 for the third part. The last part now, I consider I cut the beam at E. Argumentatively, let's say I cut the beam up at E. Or close between, you see, anywhere you cut it between D and E here, is cutting it at E. So in other words, the cutting plane line drops somewhere there. And you could consider it that way. All right. But just say that the entire span that you're considering is 6. All right. I don't know if I could get away by telling you that. Let me just say the entire span. So let's say you cut it at E, but it's right through E. Same E, right? All right. So the entire span is 8. So let's work it. Let's work it. Is the forces, all the forces, you'll have to put them in. 5 coming down, 10 coming down, those are minus. See them there. And 2 10 coming up, which are positive. Minus the shear coming down. The shear, and you'll get 5 there. So that is easy. 5, 10, 5 there, 5 there, and this. So it's how many forces that in all? About 5, right? So 5 forces coming down, and you get the shear as 5. All right, so that is easy using the sum of the Y. The moment now, anti-clockwise positive. So it's going to be, let's go again. We're going to take moment out here. Remember down here says we have our 0 point. 5 times all of that distance. So it's 5 times, they have 7 here. Right, because we could consider we cut it somewhere. Who is that? We could consider we cut it somewhere here. For argument's sake. Let's say you cut it and this is 1. Argument's sake. So you could cut it along there. For argument's sake. Right? So if you cut it there, right? This would not be 2 anymore. So it would have been 1, 2, 2, 2. So you get 7 here. Anybody follow me here? How did I get the 7 here? Anybody want to ask me how we get 7 here? The same argument that I'm talking about. Once you didn't cut it, once you cut it between D and E, we could just consider that we cut it midway here. Let's cut it midway here. So you know, so that automatically is 1. So it's 2, 3. So that gives you 7. So it will be 5 times 7. 5, 7, what, how much is that?
Got some secret cases in my own.
Someone talking?
Sir,
Yes.
so why we couldn't put it at E?
At E, it
Yeah.
won't even make sense. It will make you can't cut it at the edge. You can't cut it at the edge. That would make no sense. So you typically cut it somewhere in the span, but we're gonna just say that we cut it halfway. If you cut it halfway, you'll be cutting it at 7. You agree with that? If you cut the thing at the edge, you don't cut it. You rub against it. Right or wrong? So you cut it between DE, but you cut it specific length that you know. You don't cut it at a distance that you don't know. You measure and you cut it. Let's say it's shear halfway. If it's shear halfway is 1. So it is going to be, and it is what now? It is what type of moment you get in there? You're getting a positive anti-clockwise moment. 5 times 7. All right. So the next one you're gonna take now is the 10. So it's 10 times 5 from that distance, right? Because 2, 2, and 1 give you 5 coming from the edge. So it is, and it is going into the clockwise. So it's minus. So it's 10 times 5. The next one here is going to be which other value are we working with? So we have that we need to do this 10 coming down here now. This 10 coming down here, the distance is going to be what? 3. So it is, and it is what? Anti-clockwise, which is positive. And then the last one is going up at 10 from 1. So this 10 here times 1 is going to be clockwise. So it's minus. So, and this is plus. So that would end up and give you -5. So the 2 values that we are concerned with is these 2 values here and that 2 values here. Once you get these values, guys, you then move over now and you're able to interpret them to draw your graph. Did I bring them over? No. Let me try and get them to over so we can look at how you would draw them. See if it makes sense to you. All right. I'm just gonna try and bring the values. I'm gonna have to just copy just a little section. I want to do just the values over, and I'm going to say keep, and I am going to drop it right here. All right, let's discuss it now to see if it makes sense to you. Because some of you draw some graph that I don't know. I think it come from some space shuttle, but it wasn't related to this question any at all. So, all right, your shear force. Now, your shear force, this section we dealt with, this fraction was, x was 2. This distance was x equals to 4. This distance was x equal to 6. And then this distance was x equals to 8. So it lies between certain values. And they lie between certain values. Remember, for AB, it will be between 0 and 2. So let me write it that way, because that is typically probably how you'll see it going forward. So you'll be seeing 0, x, 2. So it's a range. And the next one will be between 2 and 4. This one will be between 4 and 6. This one between 6 and 8. Right? So that's where the values really lie. And that's how you really see them really. So the first thing you look for your shear force is -5 up top. -5 for the first one. So it comes down here. It comes down to -5 right here. So see it there? -5. And then it goes over. When it's shear force -5, then you know it's level and it come over to where 2 is. See there? All right. Remember, so the arrow goes over to 2. All right. For the section, so this was what? AB. This was what? AC. And this one was what now? Trying to remember that. That was AC. You had AB, AC, AD, and AE. Correct? So AC is up to this section here now. No, AC. Let's draw AC section in. AC, what was V? V go up to 5. So the shear force is 5. So you know, say it goes all the way up to here. Right? it covers that span right up to here, right? Arrow goes up, and the distance that it span between, it goes over to what? To 4. So you know, say it comes over here. All right, so it goes up to 5 or 4, but the span is between that. So you must put in the span. So the first one was between 2 and 4. So see the second one between here. So, right, so it come up here and it comes right down to 4. See it here? X equal to 4. The next one, it comes down to 6. You must go down to 6. It must move 2 down. What are the values, of course, at that point? -5. So if it's -5, it moves from +5 to -5. Back down to here. But it must come over 2. And I already tell you, once it's shear force and there's no load on the beam, then it's a straight line. Persons were drawing different things. If a UDL is up there, that's the only way you draw a slight line for shear forces. Remember, I gave you a slide and I show you what the rubrics of how you should understand why you draw the graph, but persons probably never look at it, right? So you come across, you go up, you just draw, it's a linear line you draw. Once there's no load on it. So you draw a line, come down, draw a line, right? It's a simple support beam, this. All right? So AB, X is 6, right here, so. And X come between 4 and 6. So between 4 and 6, you come down, -5, and you come out to where 6 is. All right. AE now, the final stage, is another 2. You're gonna come up to another 2 here. So what's the value here? Shear force is +5. If you're at -5 the last time, you go straight up back to +5. Run along here, +5, go straight up. And you're coming down 2 to 6. And you close it off there. So it closes off back right. Right? Anyway, you start at 0, it must end at 0. Right? And that is it. You can actually put a little arrow on it to show you that's the direction it maps. Coming down. All right. So you could see that the shear force is running. So look, here so what? 10. Not true? Remember right here so was 10. Right here so was 10. It shows you that this is 10. This value is 10. The shear force here is 10. There's a 10 coming down here. See there? 10 come back down. And there's a 10 going up. See there? So that is all. So all of those things help you draw the shear force. So how many force? One force come here, 10 go up. So it come out 2 and the 10 go up. So see there, the 10 reaction force come up. It come across and the 10 come back down. So you see it, and then it comes out 2. This 10 come up back. So those are actually guides. So all the force you use. So you use the forces in it, guys. All the forces you must contain. So not we just draw them isolation. So to draw this middle piece here, it is based on the force that is in the system. So it's all of them is 10, 10, 10. Right? So that is also I need to point out here. So you come out -5, but the force itself, shear go up +10. So you must go back +10, go up right up here. Right? Then you come out 2 again, it come down another -10. Shear come down. It come out another 2, but so the force is what direct with the direction that it goes every time. You have to follow the direction, and then this 2, you come right across here and you come down. So see there, 0. All right. How do I interpret now the bending moment from this? So the bending moment is there for the first one, second one. So the first one is what? M1 is -10. M2, 0. M3, it is what? -10 again. And M4, -5. But what are the distance? 2, 2, 2. All right? So let's start now. Anyway, you start, all of them you start at 0. Your bending moment you start at 0. Right? All right? So 0 and it go down to -10. So anywhere you have a line here, a linear line, in your bending moment for a simple support beam for a linear line, your graph is a slope. But in this case, it's -10. So it must slope here. So see it here? -10 go down. Remember, it's not a UDL. If it was a UDL, uniform distributed load, it would be curved. You will get a parabolic. So you get it straight coming down. All right. After that, it comes down to 2. And you slope it down because remember, this is 2. X is equal to 2 here. So you slope it down. Then it's gonna go now again. What's the next one? The next one, M is 0, so it's going back up to 0. And the distance it move is 2. So between 2 and 4, when we remember that this is between 2 and 4, so it come from -10 and it go back up to 0 at 2. Right here says bending moment is 0. Right? So that is maximum bending moment right here at that point. For AD now, coming out to D, so look where they are now. So this is 0. So see there? Come back to 0. The next one now, this is a slope again at 2. What is the value for the third section? Your bending moment is -10, right? At the distance -2. So -10 come down here and it slope down again. And it stop at 2, which is 6. Right? The next one now is going to move from 6 here now, and it's gonna go up back to 8 because look, the bending moment here is -5. Hold on, let me see. No, the bending moment work out to be what? -5 here. So it's gonna go here. Let me see. So it's come down here. This is -10. And we say -5, but it must once it reach this is even though that this is -5, which is right here. Remember, this is a representation of halfway. -5 is right here, halfway. So that's what we work out. But if you were to work it out to 8, you'll get it at 0. You'll get the bending moment right here equal to 0. Because if you, for example, was to use another expression, and I could work the problem another way, right here, and call here so X. But when I call it X, I'll give it a range between 6 and 8. That means I can put value between 6 and 8. When I work out this expression, it will tell me that the value comes here. But for your case, once this is -5, halfway, if your set come here and the slope here halfway, you can finish the slope. It must finish up at 8. Right? And that's why you need. So once it starts at 0, it must end at 0. So halfway the slope here, this is 7. Coming from down here. So that is 7, and another one will take it back to 8. And remember the values lie between 6 and 8. So that will tell you how you draw it up. Once you get in this, and the same thing, you'll be ending up back here. So that you wouldn't even have to do anything, but the distance is between 6 and 8. That's all you needed. So this was 4 marks. Once you get that, you get 4, and this was 4. Some persons just didn't do anything here. They didn't understand anything. All right. And the diagram that I will refer you to, I'll keep. The diagram that I'll refer you to, can I find it? How many persons look in their WhatsApp to those notes that I'd send you with those slides? Let me see if I just open it from here. See if it opens. Can open from here. Let's see if it will go. I just want to remind you quickly. So from here, I would have sent you something about the shear, understand the different shear. So I'd have worked out this problem a little bit different. Would include no normal, but it's very same thing. You would, let me see if I could show you what you use, some principle that you use. These, you use these here. So once it's a simple supporting beam, you will get this or your shear force. See there? And the beam would be similar to that. This doesn't have the axis here, so but it's the same thing, right? If it is a UDL, you get a slope, and the beam is curved. See them there? Once there's a load, you get a parabolic. If there's no load, you get for your shear force, you just get a regular line, and your bending moment, you get a slope, or vice versa. This is what you use as your guide. Right? So there are actually 2 of them here. See another one here, same thing. Right? So if once there are load distributed, you get a slope and parabolic. If there's no slope, you get straight lines and slope for the bending moment. This is what you use. All right. All right. So that is, you can go back to those slides, are very useful. That's what I've been using for many years now to teach the course. All right. So all right. So a lot of persons who through engineering, I have tutored them with this course for many years, writing the exam for CCJ. That's what I use, and effectively they understood the topic. All right, so let's move on to the last one. All right, so this question here, everybody should have got this. All right, we have half an hour to go. Let's quickly see if we can wind up. All right, so you got this figure here, and I figure a lot of you would have understand this, but some person messed up along the way. Any question there? I should have asked if you have any question there before I move on to this topic. Was that clear? Did it make any sense around here? Is there any question? Is there any clarity? Ask no, you know, or forever hold the guns. Hello? We're good?
Sir, I'm good.
All right.
Also,
All right.
Excuse me,
Good.
sir.
Pardon me?
So I was asking, at the end of the class, you can send the recording to me. I came
All right.
late.
All right, fine. All right. So that's what I opened up there. I referred to that and I found it right in the WhatsApp. I was able to pick it up, open at the same time and refer to it. If you don't understand the topic, run through that slide also. That slide is very effective. Right? Those are one of my basic slides that I use to teach people this topic here. And I used to work for a complex question with them, but we don't have the time in the course to get through that. So you have to do it yourself. All right, so let's move on to this one. All right, so this one you have a system here, and one of the first thing I can say to you, you need to let's look at what it asks. So it says one, it gives you thickness and density. So from that, you know that you're going to find the mass. And a lot of one person mess up. I saw one person writing the thing very well, but just not writing nonsense in the end. All right. I saw somebody writing something for mass and I couldn't believe that they didn't remember the density formula. But it happens, right? So you know the mass is going to be density times volume and not density divided by volume or something. Rather than they have it multiply and they divide the density by the volume. So remember, density is mass per unit volume. Once you remember that, you can remember the definition and remember the formula. It is mass per unit volume. And that is very basic, right? I remember that right from high school. That's what you just keep that in your head. Mass per unit volume. So you know mass come and it is per division volume. That's what it means. That's what the formula says. You just remember. That's when I was doing O-level physics, right? Class. And that's what we use to remember it. Very basic. All right, so let's go again. It says here, determine the area of the shaded area. And this was what you need to do is to separate it into different regular shapes, all right? Then you find the mass. Once you have the thickness, you can find the mass because you know that volume is area times thickness, right? So you get the area, total area, times the thickness, and then that you have it. And you would have converted your thickness to meters from foot, right? Because you have the conversion factor there, right? It means that you're gonna convert also your area to meters square, right? In the end, to get a unity of meters cube, all right? And then the meters cube, we cancel meter cube, leave you with kilograms. So you have got the kilogram mass. All right. So let's say now we divided this figure. That is 1. You end up now with a square. This thing don't look like a square, but it's a square. All right, so let's move over to where we have it. So the first thing, you drop a line here. You got a square, right? Trying to get that right. Where is my change of color? Hold on a second here. Why am I not able to change my color? Something is not. Right. So as I was saying before, somehow I can't change it right now. It's not allowing me. I don't know what's happening with the configuration. Something is shadowing the device. I can't change it. The icons is just being hidden. All right. Let's move on. See, I'm gonna write with the red one, even though it's in black. I can't change it. All right. So you have you're separating to the different figure. First, you do the square. Look, see the square here? Right here, this is a square because this is 3 and that is 3. All right. So you look at the figure and then you're able to pick it apart. The big circle is just half a big circle. So see it here? The radius across here is 1.5, 1.5. So you know your radius is that. All right. This, you have a circle, which is going to be the negative area, right? So that's the negative area. What's the radius of that? That is 1, not 1.5. So look at them. They all work out here. Let's look at them now. So the area for the square is 9 feet square, 3 times 3. The triangle is half base times height, 4.5. And the semicircle is half of area. The radius for the semicircle is not a full circle, is 1.5 also. And you divide that by 2, you get 9 upon 8 pi. And the semicircle is a negative area, which is negative pi, because it's 1 square, so you get negative pi. So you get all of that, and that would have given you a significant amount of marks for the first part. Let me see, you would have gotten 4 marks for that, and then you use the formula for density, but you have to do the conversion, eh? You just convert this but once you have this, all I would do is square this. So 1 meter square is equal to 3.28 square. Whatever square that equal to, and you just use the ratio and proportion, and you calculate that. So I won't even demonstrate that here. I'll leave that to you. Right? So you just 1 meter square, you square the side. Let me just show them. 1 meter square. So you square everything here, equals to 3.28 feet square. So you end up with 1 meter square, and whatever value this work out to be, 3.28 square feet square, right? So you square feet. And then now, when you finish with that now, you're going to do the thickness is 1 meter, one meter, you know, say, what was the area that we have here? The value we have here is 13.89, right? So 13.89, you put 13.89 feet square, and you convert it to see how much meter that is, and you cross multiply, and you do the same thing. You're going to divide, you're going to convert this to meter, and then you work out that, because you know what meter is equal to that, and you convert this one, right? And you multiply both of them, and then you use that now to multiply times the density, right? So I won't demonstrate that. That is easy. All right, so you're gonna work out. All right, so let's get back to the last piece here. So now after you have worked out that, let me just remind you, firstly, how you find X and Y distance. So for the square, you would have had this distance. Halfway is right at the center, 1.5, right? Halfway is 1.5 up, 1.5 to the X, and 1.5 to the Y. So this is 1.5, that is 1.5, right? So you would have found them easy. That's half of 3, 1.5, and both for X and Y, half of them 1.5. So that will map you back to the origin, which is right here. All right, for the triangle, how many of you remember that is 1/3 the base and the height? 1/3 base, 1/3 height. So 1, 1, 1. But then now the distance from this one here down to the origin is gonna be 4, because it's 3 plus 1 give you 4, which is this value here. Come on. And then 1 is the Y distance. So the Y distance is 1. Right? 1/3 of 3 is 1. 1/3 of, right? So you see them? Any question there? Any question there, guys? So 1/3 of 3 is 1 plus 3, give you 4. All right. Next one. Where's the next part now? Oh, so for the semicircle now, you'll have to remember this formula here. So it's going to be 4 upon R 3 pi. It is minus this distance Y here, because so it's some distance here, some line across here. That's equivalent to that X distance. Sorry, this X distance here is some distance across here, which give it by this formula here for the X. But it is minus because it's over the negative of negative side. So it's minus 4, 1.5 divided by 3 pi, you're minus 0.6. So it's minus 0.6 somewhere over here, running along there. Some distance over here, minus, right? Whatever distance is that, this is minus distance here. So it is right along there. And then y. Sorry, guys, one second. Okay. I heard some noise and I had to just check. Sorry. All right. Make sure that I'm locked in. All right. So hear me now. So you have, where are we now? We are here. So half of the a section of the pi, which is 4 upon r, 3 pi of that circle here, you use that formula there. Remember that formula. It's on your sheet. You don't even have to memorize it, right? But you need that distance. So you find that distance there. What about the y distance? The y is going to be to the center of the circle, so it's going to be 1.5, right? So this distance will not change for that. For the circle is 1.5, but this is your x distance, which is 4 upon r 3 pi, right? And you get that value there. All right, what about the circle? The circle has a negative area, so that's the only reason why I have a negative there. The circle here now have a negative area, right? What is its center? Its center for the circle, for the x distance is going to be 0. Because the origin is at the center is at the origin, so it's 0. Right? And for the y distance is 1.5. And as simpler you do to get xa, you multiply the distance x, whatever distance x times the a distance, and you get xa here and similar xy. And you simple sum them, and then you take for the x, the sum of x divided by the total area, get that value. The sum of this here times divided by the total area, and you get 1.3. So x distance, and then the last part of the question, you're asked to show where is the diagram. Did I do that part? No. Let me just. So all you would have done, see if I can find that slide to show you. Part of the slide. Where is it? So this is what it would typically looks like. So it typically would looks like this. All right. I just drop it here. So all you do, you'll map it back to x is 2.10, and then you show that the y is 1.33. So you take it from there and just map it. That's all we asked for. And then you would have gotten some marks there, 2 marks of that. All right. So that is exactly what was asked for. And you would have gotten your test, full marks in your test. Just a few persons were able to inch out good marks. Most persons were somewhere average. And this is my reason for really calling you all to highlight some weaknesses that I'm seeing here. This question should be good. Most of you, if you concentrate, you do that question well. Please, the person who mess up the density part, I hope that the person is here. Do not mess up that density formula and thickness. Go back and look at it. I didn't go through it fully, but you should be able to do that. You should be able to find the thickness, convert the 1 millimeter here to meter, then convert the, right? And once you convert that thickness to if it's millimeter, you know that is 1 times 10 to the minus 3 that will work out to. So that time, whatever conversion you get here, and your answer should be about 10. So I can tell you that already. It's 10. The mass is about 10 point something kilograms, right? So you would know the answer there. I won't say anymore. All right, I will share the slide, the recording with you, right? I think I will drop it. Yes, I will save it and drop it on my YouTube channel, and then you can watch it there. Hello.
So, what's the channel name?
Well, once I send you my link, I'll send you the link of the video, and you will see it there. You'll be able to watch it there. So it's in my name. I have not even really been showing it off to a person, but quite a lot of statics stuff is there. I also engineering physics, but mainly statics. You have quite a bit covering different topics in statics. right?
So, and you said you were gonna send the slide as well?
No, I'm not gonna send the slide.
Oh, okay.
I'll just send the video. I don't have it's not my privilege to do that. Right? So I will not share this slide. I'll share you the video that you can reflect back, but I will not send the slide. Right? I didn't have the slides
yes,
are
sir.
not mine, so I won't share them that way. All right. So I trust that you all was able to get something from the revision, and just guys, do your best. You have to do some work though. You have next week. Which day you have your exam, please? Which day you have your exam?
The second, sir.
Pardon me?
The second.
You did one set already?
No, I'm saying it's the second of me.
2nd of May. Okay.
Yes.
What format you said the exam is in again?
I don't remember the exact number, sir. I have to look back at the picture, but it was both multiple choice and word questions.
Multiple choice and word question. Oh, okay. All right. That's good. It saved me. I will have a lot of papers to mark. All right. Thanks. All right. Good. So, all right. All the best, guys. I wish you the best. I'm compiling the workshop grades now. So, well, you won't be able to see that until when final grade. But most persons are doing good in the course, in the workshop course. So, no worries there. And you all saw your grades, right? So, trust that you are okay. All right. So